hints for the review packet. We're now on the part that says it's 9S Thermochemistry Summary, and it's the 1 through 8 that were towards the back of the packet. So some pointers on this one. The first one was sketch fully labeled enthalpy diagrams for two different things. The first one is going to be a single step reaction that's exothermic, and the next one is a two-step reaction, which the first step is going to be exothermic, and the second the overall reaction is going to be endothermic. So enthalpy level diagrams are when you're going to have this energy versus reaction progress. And so you're going to be showing how much energy your reactants have, how much energy your products have, and I can see there I put in a lot of energy to break the bonds and a little bit of energy came out, so you can figure out if that's endo or exo. If you had multiple steps, you would just have to say, and I'm not giving you the answer all the way, I'm just giving you pointers, so if you just copy this, you won't have the right answer. This one, let's say my reactants start here, I break bonds, I form bonds, there we go. Break some more bonds, form some more bonds. Okay, so this is putting in energy, getting the energy out, that would be the first step. Putting in a little energy, get a lot of energy out. So I'll go ahead and tell you that this first step that I made was endothermic because I put in a lot of energy and I got a little bit of energy out. And that second step is going to be exothermic because I put in a little bit and I got a lot out. Overall, it's barely exothermic because I'm going from here to here. So you can go ahead and draw your diagram to make sure that you have something that matches what they want, because I didn't match it. I'm just showing you how you can put multiple steps in an energy diagram. For number 2, you're given the enthalpy of combustion of butane. So that means if you're taking the butane and you react it with oxygen to make carbon dioxide and water, for every 1 mole of butane you combust, you give off 2,881 kilojoules per mole. I'll have you, I believe everybody knows what the significance of the negative sign is. I'll give you hints for B. So B is calculate the enthalpy change when you have 400 grams of butane. So we have grams, but the balanced chemical reaction doesn't relate grams, it relates moles. So convert grams of butane to moles of butane, and then use your equation to say for every 1 mole of butane, I give off this many kilojoules. So you're going from grams of butane to moles of butane, and then moles of butane combusted to kilojoules given off. For part C, you're going to use your answer from part B. So in part B, you calculated a certain number of kilojoules. Part C says we're going to use this specific heat of water, 4.2 joules per gram Kelvin. And you have a reaction where, or you have an instance or situation where only 63.15% of the heat that you produced in part B is going to be going into here. So you know you're going to have to calculate 63% of your answer from B, and that's going to be joules, because we calculated in joules. So now you have an amount of heat. So we have a heat. You are given a specific heat capacity. You have a mass of water, and you are asked to solve for the change in temperature. I believe you know which equation to use. The biggest problem here, watch your units. Make sure you're only using 63.15% of the joules from part B, and then be careful because I've got kilograms here, but I have joules per gram here. And your answer here, actually you'll probably calculate it in kilojoules, but then you have this in joules. So make sure you convert so you're using the same units throughout, otherwise you'll get the wrong answer. If you're off by a factor of 1,000, you know why. Another thing to think about is your change here is negative in B. In part B it's negative because the butane's giving off heat. And then in part C we're saying that that heat goes into the water. Now we have a positive change for the water. So your temperature should get hotter, your temperature should increase if you're adding heat. Then part 3. This question concerns the compound carbon disulfide. Using the data below, calculate the enthalpy change for a reaction between carbon and sulfur to form carbon disulfide. Okay, so we know what our goal is. Our goal is going to be what is the change of enthalpy when carbon, as a solid, reacts with sulfur to form carbon disulfide, S2. Okay, and this guy, really? about for now, but we haven't talked about allotropes and how these things tend to exist. So you have your goal. What is the change of enthalpy for that? You have the delta heat of formation forming. So when you react sulfur plus oxygen gas to make SO2, this is the enthalpy of that reaction. You're going to have to write out the reaction just like we did for number 4. And here's the heat of formation for carbon dioxide. So you're forming 1 mole of carbon dioxide from carbon as it exists in its standard state, solid, and oxygen in its standard state, gas, to make carbon dioxide. And you're also given, this one's different, this is the change of enthalpy of combustion. So combustion, carbon disulfide plus oxygen, and the two products will be carbon dioxide and sulfur dioxide. So please write out those equations so you'll have the steps. You have your goal reaction here, you'll have your 3 steps, and you'll be able to say, I need this as a product. The only place that shows up is going to be in this step. I can see that I have this as a reactant. I'm going to have to flip that step, flip this sign. If you write everything out, I promise you have a much better chance of getting the right answer, even though it's a little tedious.